Welcome again. In this session, we are going to give an example on how to resolve forces by applying Newton's second law of motion. So we have a traffic light weighing 100 newtons, hangs from a vertical cable tied to two other cables that are fastened to a support. So this is a support. So the upper cable makes an angle of 37 degrees and 53 degrees with the horizontal beam. So this angle is 37, this other angle is 53. Find the tension in each of the three cables. So we have this cable, and then this other cable. So the assumption taken in this problem is that these traffic lights, this system is at equilibrium. So when the system is at equilibrium, then the net force is given by 0 because this traffic light are assumed to be at equilibrium. Traffic lights are at equilibrium. So meaning that this rope tying the traffic lights is not accelerating. So solution. So we'll say that we construct a diagram of the forces acting on the traffic light and a free body diagram for the knot So the knot you're referring to, this knot here. For the knot that holds the three strings. Or three cables together. Now you see, in this given diagram, there is tensional force acting downwards, this T3, and then actually there's a force acting upwards, and then there's a force acting downwards, which are actually proportional or have the same value as this T3. So we'll draw, if we draw a parallel line to this support here, then you see the support and this line I've drawn here are parallel. So if this angle is 37, so it means that this angle will also be 37. And then if this angle is 53, then this is also be 53 degrees. Let me call this angle alpha. So I'll draw a diagram representing all those forces as, so if I take this, this node, this to be my x, y axis, so this is my x, and then this will be my y axis, then I'll have this diagram representing all the forces. So let me have this. So this is my y-axis. This is my x-axis. So we have these cables So we have this cable. Let's say that the tensional force here is given by, because this cable is called T2, let's call that force tensional force T2. So this angle is 53 degrees. And then there's this, because the cable was called T1, let's call that tensional force T1. And then there's this cable labeled T3. So let's call that tensional force T3. This angle here is 37 degrees. Let's call this 37 theta. Let's call this angle alpha. So the interest is now to resolve these forces in this diagram. So this way you have the knot. This knot, this diagram here. So this is the knot. Now, if we draw right angles to these forces in this diagram, so I draw a right angle triangle here. I draw a right angle triangle here. So this is the direction, and then this is the direction. And then this is the direction, and then this is the direction, upward direction. So using Oshachota, then you should be able to see that this vertical component at this point will be magnitude of T2 force will be T2, and then this being opposite will be half sine of alpha. Remember, I've called alpha to be 53 degrees and theta to be 37 degrees. And then this one will be T2 cosine of alpha. This one will be T1 cosine of theta. And this will be T1 sine of theta. So by definition, because this system is assumed to be at equilibrium, then the acceleration is zero, so which means that net force is zero. So let's analyze the forces in the x direction and y direction independently. So x component, when we say component, we mean horizontal. So forces which are acting in the horizontal direction, now we take going to the right is taken to be positive, going to the left is taken to be negative, going up is taken to be positive, going down is taken to be negative. So that's the convention we take. So forces acting on the horizontal, we have this force T2 cos alpha, and then because it's the direction to the right, so we take it as positive. So T2 cos alpha. This other force T1 cos theta is to the left, so the sign is negative. So T1 cos theta. Those are the only forces which are acting in the horizontal direction. So that should give us 0. That's to say, i.e., T2 is the same as T1 cos theta over cosine of alpha. I've simply taken this to the right. So this T2 will be the value of this. So it is the same as T1 cosine of theta is 37. And then cos of alpha is 53 degrees. Then, which you can actually simplify, cosine of 37 divided by cosine of 53 is 1 point. So we'll have T2 equals to 1.32 822 T1. So we call this one equation 1. And let's resolve y component forces or the vertical forces. So forces which are acting vertically, we have three forces: T1 sine theta, T2 sine alpha, and this T3 acting downwards. So we'll have T3, which is now going down, we take its negative, going up is positive. So we have T1 sine theta plus T2 sine alpha, this force, and then minus T3 should give us 0. T3, remember from the question, the weight of this traffic light is 100 newtons. So this is the same as saying T1 sine of, so theta is 37 degrees, plus T2 sine of 53 degrees equals to T3. So taking this to the right hand side, and the weight is 100. So now using equation 1 in equation 2, so we'll have, where there's T2 we replace by this, so we'll have T1 sine of 37 degrees plus, where there's T2 we put 1.327044822 T1. You multiply by sine of 53 degrees, should give us 100. Actually call this one equation 2. So I'll replace 1 in 2. So simplifying this, so we'll have T1, so that's sine 37 is 0.6018150 T1 plus now 1.327044822 times sine of 53 give me 1.059825118 T1 is equals to 100. So adding this and this, we'll have plus 0.6018130.232. I get 1.661638141 T1 equals to 100. So then I divide through by this value 1.661638141, 1.661638141. So 100 divided by answer, I get T1 to be 60 point. T1 so this just a minute. Yeah. So T1 to be 60.1815747.4 newtons. Now to get T2, so T2 will be given by, so from this equation 1, it is 1.3 times T1. So when you multiply that one by, so take this value times what you have gotten as T1, so times 1.327044822, we get T2 to be 79.86364.714 newtons. And then T3 by default is 100 newtons, which is the weight of the sign post. So this is how the weight is acting. It's a weight of the traffic light, 100 newtons. So that is how we're supposed to solve that particular problem. Thank you.